All right, welcome everyone. In this video, we're going to be reviewing some key concepts from civil engineering materials as well as the engineering mechanics of materials course. Specifically, we're going to be hitting some examples from stress and strain, so looking at some concepts and also how to read information from a stress and strain graph. We're going to be doing some example problems from Poisson's ratio and Hooke's law, as well as one example problem from phase diagram. So let's review some of the material concepts, specifically some of the jargon or just key terms that you'll see throughout this course and in your civil engineering materials course. So like one of them being the brittle and ductile materials. So how would we distinguish between brittle and ductile materials? And when you see these words, always think of discernible deformation. So a brittle material is one that will fail with little to no deformation, or a ductile material will generally experience elongation or strain before reaching that rupture point. Now, these are normally qualitative properties, so it's hard to actually define a set percent elongation that would distinguish between brittle or ductile. But just think generally in terms of material. You know, concrete is going to be a brittle material, a ductile material would be steel. Anything that will have a significant amount of observable deformation before rupture or failure is going to be ductile. All right, so the next part, how is elastic limit and yield strength related? Now in this, I remember in class we said kind of focus on just the whole civil engineering side of things, not necessarily the material side of or material science side of things. But conceptually, elastic limit and yield strength are technically the same. However, the exact elastic limit of a material is difficult to find. So civil engineers, we use like tension tests and the UTM to create a stress strain diagram. But remember that stress strain diagram is just a bunch of discrete little individual points tied together with a function or a line. So that yield strength is this arbitrary estimation of the elastic limit using either this 0.2% offset or 0.5% extension. And I told you in this class, focus mainly on that 0.2% offset, because this is the thing that you'll see the most. So next part, explain the difference between elastic and plastic behavior in materials and give examples of each. So first of all, just being a material, you know, anything, most materials, all materials will deform when stressed. So they'll experience some type of strain when a load is applied. However, elastic behavior means that the material will fully recover all of its deformation when unloaded. So it'll go back to its original length or shape or whatever it was before a load was applied. Plastic behavior, however, will result in some type of permanent deformation when unloaded. So some permanent strain or permanent deformation once that load is removed. So just graphically, you know, if we had stress versus the strain here, elastic, we load and unload, it goes back to that 0 point showing here, zero stress, zero deformation. If we had plastic behavior, when we load and unload, although we're on the y equals 0, so no stress, we still have some permanent deformation or permanent strain that's captured there. Okay, so define Hooke's law. Hooke's law is the relationship between stress and strain in Young's modulus for a material that is homogeneous, isotropic, and elastic when loaded triaxially. So generally what we'll say here is that this Hooke's law is the relationship here showing a linear relationship when our stress is less than our elastic limit or our yielding strength. So in this case, for our three-dimensional Hooke's law shown here, you have Poisson's ratio. For one-dimensional Hooke's law, that's just that the Young's modulus E is equal to the slope of the stress strain curve in the linear elastic region. So E is equal to stress, sigma, over strain, epsilon. So let's look at some examples of that stress strain. So in this one, a tension test was performed on a specimen with original length of 10 inches and a square cross-section of 0.25 inches. The specimen was loaded until failure, and the material's axial deformation was measured at 2 key stages, and they're shown in these tables below. So we see the start 0, 0. That's what we expect, right? 0 load, 0 deformation. We say we reach this elastic limit of the material at 35 kip, and we have a resulting deformation of 0.092. And then we have failure at 75 kip, and that is at a deformation of 1.15 inches. We're asked, what is the material's modulus of resilience? So we'll first have to think about what modulus of resilience actually represents. But what we first need to look at is the data provided. So we see that the load is in terms of a kip. And remember, a kip is 1,000 pounds. So that's the load that we're given. Everything that we've been talking about so far is going to be stress and strain. So first, we should note, like, we are going to need to calculate the stress at each one of these 3 key points, or really just 2 key points, because 0, 0 is not going to have any stress or strain. Also, with the deformation being in inches, and a kind of a hint here that we are given an original length of 10 inches, we're going to have to calculate the resulting strain as well. So strain is a normalized deformation over the original length. So it's the deformation divided by the original length of the object. So what exactly is the modulus of resilience? This is the energy the material can absorb within the elastic range, or the maximum amount of energy it can absorb before the material is pushed out of the linear elastic region. So what this actually represents in engineering terms is this is the area under that stress strain curve in the linear elastic range. So as I said before, we're given load, we need to calculate the stress. So the cross-sectional area is given, we're told that it is a square cross-section with 0.25 inches thickness. So our area is going to be 0.25 squared, or 0.0625 inches squared. We also need to calculate the strain. We're given a deformation data, but we need to divide that by the original length, ensuring that our units are the same here, inches over inches, and our stress will be KSI. We're left with this data set here. Now, you're not asked to do this, but you could plot this. And this is, a stress strain graph where we just have 2 linear functions defining the linear elastic and then this plastic range. And the plastic range is one thing, but what we're asked for specifically is that modulus of resilience. So that's going to be this area here highlighted. Now, if we show this in equation, that's 1/2 base times height. So looking at the units here, we have strain, which is unitless, and then the stress, which is 560 KSI. And so what we're left with is this modulus of resilience in terms of KSI, which I know is not an energy term, but this is just civil engineering 101 kind of stuff. So we're not going to look at this in terms of unit volume, energy, or anything, but we're left with a value of 2.576 KSI. Now let's just say, what if they asked for toughness instead? Now toughness is the same thing. We're looking at energy, but instead of the linear elastic range, we're looking about the energy that it can absorb before it fails. So this would be the entire area under the stress strain curve. So for this, we would have to divide this into different segments. We have the original triangle, we have the rectangle, or you could do a trapezoid, either way, but you would add the total area up and to get the total toughness. And again, that would be in the same terms of KSI. Okay, another stress strain problem. This tension test is performed on a metal specimen to fracture. So this point here is failure point, and it's producing the stress strain relationship shown below. Estimate the following material properties from the graph. So 1 being the modulus of elasticity, the 2, the yield stress using the 0.2% offset method, and then 3, the secant modulus at a stress of 70 KSI. So the modulus of elasticity, remember the physical meaning of this, the slope in the linear elastic region. So what we do is we just find 2 points, using 0, 0 is always a good point. And we have to remember what the slope is, how to calculate the slope from this. So rise over the run, or you pick 2 y coordinates and the respective x coordinates, or 2 margaritas over a picnic table, if that helps you remember it too. Well, anyways, so for the modulus of elasticity E here, we'll just pick 43 KSI and its resulting strain of 0.002 inches over inches. And what we see is KSI is the only units here. So our E value, our Young's modulus, or our modulus of elasticity, this will be about 21,500 KSI. Now the yield stress using the 0.2% offset method, remember what the 0.2% offset, first we look at our x-axis and we are in inches over inches. So we need to convert this 0.2% back into the units that we can use here. So we divide this by 100. So we find 0.002 inches over inches on our scale, and we follow using the same slope as the Young's modulus until that intersects with our actual stress strain line. So once this intersects, we read over, and whatever our y-axis shows is going to be our yield stress. So in this case, it'll be approximately 73 KSI. Now this last one is the secant modulus. Modulus, in this case, we're still talking about slope. So secant meaning it's starting at 0, 0, but then we have the other key point that we find the slope to at 70 KSI. So we find where 70 is on our stress strain curve, and that straight line between those two, the slope of that straight line is going to be our secant modulus. So we have 70, the resulting strain there is about 0.0045. And so our secant modulus is about 15,555 KSI. Now secant modulus in this case is an underestimation of stiffness compared to our linear range, or our Young's modulus, modulus elasticity. Okay, another one here. Material has a yielding stress of 36 KSI and a strain at yielding of 0.5%. If the original length of the tested specimen is 5 inches with a diameter of 0.6 inches, what is the total energy that the material can absorb before there is permanent deformation measured in the object? So the few key terms that we have to notice here is that term total energy again. So when we think of total energy, think of area under the curve. The other aspect of that is before there is permanent deformation. So there's different ways to word this, before permanent deformation, keeping it within the linear elastic range. But essentially what we're talking about here is the modulus of resilience. So similarly to 2 examples ago. Remember, the modulus of resilience, don't get caught up with that first term modulus because there's modulus elasticity and everything. Think modulus of resilience and toughness are the 2 things that are the area under the curve. So this is the area under the curve in the linear elastic region only. So we're not given the actual data here or a plot, but you could easily plot it just to visualize it. We're told that the material has a yield stress of 36 KSI with the resulting strain of 0.5%. So we know this is our 36 KSI. The resulting strain is 0.5%. But we don't show this terms in percentage. We need this in units over units. So this will be 0.5 divided by 100, so 0.005. And the original length and the diameter really is just kind of to throw you off here. So this information might be needed for another part of the question, but in this specific case, we're given all the information we need. All we need to find is that area under the curve right here in this triangular section. And obviously it's a triangle, so we know the area of a triangle, 1/2 base times height. And then just plugging all of that in, we have our base will be the x-axis of 0.005. And then our y-axis here, the height is going to be 36 KSI, which is our yielding stress. And so the only units here are still KSI. So this would mean our modulus of resilience is 0.09 KSI. Again, KSI units for this course will just be fine in terms of energy output. Generally, what you'd do is you'd give some volumetric value and then translate this KSI per unit volume, and then you might be able to translate that to some energy like BTU or joules or something. All right, let's look at this conceptual one here. So describe the process of creep by drawing the input and resulting strain over the time. Label all the sections of the curve exactly, and also to list some examples. Remember that creep, it's a weird term because it's something we've all heard, but not in terms of civil engineering. When you think of creep, think of constant load, slow deformation. So it might be easier to think of some examples of this. Think of like a asphalt material or something that is like I mean, one of the better examples, which you'll cover later, is consolidation of clays, which kind of, just to summarize that in itself, imagine you have a water balloon with a bunch like that's tied up water balloon, and then a bunch of little small holes poked in the water balloon. Let's say you put a like a paperweight on top of the water balloon, and the water can only escape through those small little holes. So the load is constant, but the balloon doesn't deflate right away. It takes time for that water to remove from the holes. So same thing with other materials like asphalt and soil and even sand. Essentially what we have is a constant load over time, but the strain does not occur simultaneously. The strain will slowly increase, although the load is being held constant. So if we're drawing a constant load, we start at 0, let's say, and then we just apply some load for a constant time, pretend that's an actual straight line, and then let's just say we remove the load back to 0. So this is as a function of time. So obviously looking at the strain, when there is no load, there's no strain, but as soon as the load is applied, we don't see instantaneous strain. Rather, we see a slow increase of strain as long as the load is applied. And then whenever the load is stopped being applied, then we see a slow rebound. Maybe that's a little bit more concave, depending on the material like that. So what we see here is this essentially elastic recovery will be that initial section. And the creep is occurring here where the load is constant. So some of the materials that we see, a lot of materials do have experienced some amount of creep, but the ones that experience the most will be soil, asphalt, sand and clay, and some concrete. All right, let's move on to some Poisson ratio questions. So this one from a homework here. The resulting block shown below, it's subjected to tension within the elastic range. That's going to be a key, good assumption there. The increase in length in A, so that section shown there, is going to be 0.002 inches, and the contraction of B is 0.00325 inches. So really, really small stuff. And the original length of A and B are 2 inches and 1 inch respectively. And let's just say this is a multiple choice question. Which of the answers below is most likely the Poisson's ratio of the material given this? So the Poisson's ratio, remember, this is the ratio of the lateral strain divided by the axial strain. And that negative is there just to account for the change in direction of strain. So one strain will be a contraction while the other one is an extension, or vice versa. So remember that with the Poisson's ratio, the expected range will be from 0 to 0.5 for civil engineering materials. And let's just go over what physically this means. So for a 0, this means no lateral deformation when it is pushed or pulled. So if we were applying it in this direction, let's call that the axial direction, what we would see is an axial deformation, but no resulting lateral deformation. So an example of this would be like cork or some type of material with a lot of void space. Essentially what this is called then is a perfectly compressible material. So on the other end of the spectrum, 0.5, this is perfectly incompressible, which means there's no volume change. So examples of this would be water, rubber, hydraulic oil, or something like that, where if we load it in this axial direction, we see an equal and opposite direction in the lateral direction. Now, the reason it's 0.5 is because you're only looking at one direction, so it's counted in that way. And it's actually technically occurring in 3D, so there's one coming in the Z direction as well, but we don't account for that. So 2D, it would look something like that. But it's important to remember those two bookends of it. 0 being perfectly compressible or fully compressible, and then 0.5 being perfectly incompressible. The key thing with 0.5, zero volume change, where the 0.5, or sorry, Poisson's ratio of 0 is maximum volume change. So I guess you could, equals max here. So let's say these are your examples, on the FE or something. So right off the bat, we know the answer should be 0 to 0.5. So we already see one at 1.13. Remember, we can just kind of get rid of that one right off the bat. What we also see is we observe a deflection or a deformation in the A and the B direction. So we know that the material is not a Poisson's ratio of 0. So we can get rid of that. So it's just really between these last two. So let's actually calculate it here. The axial direction is the direction at which the load is being applied. So this is our A direction. So 0.002 divided by 2 inches, always ensuring that those inches over inches or the units are correct such that they cancel out. So we have 0.001 inches over inch. For a lateral strain here, same thing. I'm just putting that negative in there because we know that's going to be a contraction and the other one is going to be an expansion. And then we're at this really, really low number here. So the Poisson's ratio, we put these numbers over each other. Remember, it's always lateral over axial. It should spell out la, like la Poisson, something like that. And what we have is the 0.325 or 0.33. And we can pick our answer there. So see right off the bat that we were able to remove two of our potential answers, just knowing the theory of Poisson's ratio. Okay, another Poisson's ratio one. So a metal rod with 0.5 inch diameter is subjected to 2,000 pound uniaxial tensile load. Calculate the resulting diameter of the rod after loading. Assume the modulus of elasticity is 10,000 KSI, the Poisson's ratio is 0.3, and the yield strength is 21 KSI. So essentially what we have is this 0.5 inch diameter rod subjected to this tensile force, 2,000 pounds. And we know that the resulting will have an extension in the axial direction and a compression in a lateral direction. So we are asked to find the resulting diameter. So we know that this resulting diameter, we're going to call this D2, or the second diameter of that we care about. This is equal to our original diameter, D0, plus this change in diameter. Now remember, Poisson's ratio is going to be the key thing here. But we'll also need our Young's modulus. Our Young's modulus is going to translate between our stress and our strain. Now remember though, this Young's modulus is only if our current stress is less than our yielding stress. So we will have to check that because it is not told to assume that it stays within the linear elastic region. Now just to recap, stress is not given to us in this case. We're given pounds, so we will have to calculate stress. And then strain is also not given to us. We're given well, we're not given a deformation, but we're going to have to use the strain in the Poisson's ratio to find this deformation. So let's see what's given. We're given the original diameter, 0.5 inches. We're given the load, so this is in pounds, so this is a force. We're given a Young's modulus, and we're given the Poisson's ratio. We're also given the yield stress, which we need to check as well. So first, let's calculate the current stress from this 2,000 pounds and see if this is below our yielding stress. So if it is below our yielding stress, then we can use our Young's modulus to find our axial strain. Once we find our axial strain, we can use that and our Poisson's ratio to find our lateral strain. And once we find our lateral strain, we can use that and our original diameter to find our change in diameter. And of course, after we find our change in diameter, we can find our second diameter. So let's go through that. First, we need to calculate the area of a circle since it's a circular rod here. Be really careful. We're given diameter, so radius, pi r squared, just divide by 2. And you get an area of 0.196 inches squared. Now the axial stress, or sigma here, is going to be the force, or 2,000 pounds, divided by the area. We just calculated that, so our stress will be 10,204 PSI, pounds per square inch. So luckily this is still under our yielding stress because our yielding stress is KSI. Remember, KSI is kips per square inch. So really, this is equal to 21,000 PSI, pounds per square inch. So we're still within the linear elastic region, which means we can move on to our Poisson's ratio. So our Young's modulus, or Hooke's law here, our Young's modulus is stress over strain. So we can find and rearrange this equation to find the strain. And so this is going to be, 10.204 KSI, and make sure that the units cancel out KSI over KSI. And what we get here is this strain is 1.02 times 10 to the negative 3. Now remember though, this strain here, this is technically our axial strain because we're talking about our axial stress here. That sigma is going to be our axial stress applied. So now that we know our axial strain, we can use that in the Poisson's ratio to find our lateral strain. I'm just going to keep the negative in here, but remember the negative is just representing that decrease in value. So it's the compression or I guess it's compression, the negative value of deformation. So that we can calculate the change in diameter, knowing that this is equal to the original diameter times our lateral strain. So that's literally just taken from this equation here, but instead of length, we have diameter. Instead of that little delta, I'm just putting in delta D for that change in diameter. So if we do this math out here, we get a pretty small number, which makes sense. So essentially, this is a negative value, but just remember what this actually physically means is it's just 0.00153 inches in the opposite direction as the axial strain. So this is our compression. So the new diameter, D2, this will be 0.5, which was our original diameter. And then we know it's going to be in compression, so that's minus 0.00153 inches. And so our new diameter, not that different than our original diameter, but very small loading here. So we just have a very small decrease, but it's 0.49847 inches. All right, another one here. This time we're told it's a copper rod with a diameter of 19 millimeters, modulus of 110 gigapascals, and a Poisson's ratio of 0.35. It's subjected to tension within the linear elastic region, so we're already given that, so that's kind of nice. We're asked to determine the force applied that will produce a reduction of the rod's diameter by 0.003 millimeters. So a few things to note here. We are in SI units. And remember here, we're given millimeters, and remember what a Pascal is. Pascal is a Newton over a square meter. So we're going to have to keep an eye out to convert those millimeters to meters at the end of it when everything's all said and done. Now, with this one being very similar to the one before, we're trying to find this change in diameter, but we're given the rod's diameter, or the original diameter change. Remember that diameter is lateral, reduction is that change in diameter, and then the force that's being given here that we need to find is going to be axial. Let's set it up a little differently this time around. So let's actually keep all the variables together and see if we can produce a function that will actually, then we plug in everything that we are given at the very end. So we know we're going to use the original equations from last example too, Poisson's ratio, Hooke's law, and we're told that it's already in the linear elastic region, so we don't necessarily need to check that the axial stress is less than the yielding stress. And it's kind of nice because we're not given a yielding stress anyways. Now remember though, we're asked to find the P, or the force, the load, that will be in newtons. So we need to keep an eye out and ensure that our final answer is everything cancels out such that we're in newtons. So our lateral strain, this is exactly from before, change in diameter divided by the original diameter. Our axial stress, sigma, will be the load P that we're trying to find divided by the cross-sectional area. Our axial strain, given our Poisson's ratio, we just rearrange this and solve for our axial strain. And plugging in our lateral strain from here, this equation, plugging it here into our numerator, and then moving that D over, we have the equation shown here on the right, that axial strain is equal to the negative change in diameter divided by the original diameter times the Poisson's ratio. So just to keep it constant from before, I was showing D naught. So that's our original diameter that we're given here, 19 millimeters. So looking at the Young's modulus, since we're in the linear elastic region, we can solve for our stress, just from our stress, sigma is equals force, or P divided by A, and then the axial strain, since that is axial direction, the same as before, so I'll just put that knot there. And so all we now need to do is just move this equation around and solve for P. So looks kind of gnarly, those X's, that's just multiplication, but we're given everything here that we know already, right? We're given that we can find the area because we're given the diameter, we know it's a rod, so find that. We're given the Young's modulus of 110 gigapascals, so giga is times 10 to the 9. The change in diameter that we care about is 0.003 millimeters, so I'm just going to go ahead and bump that up to meters here, so 3 times 10 to the negative 6, millimeter is 1/1000th of a meter, so we divide that by 1,000. Same with the original diameter. So if we have the original diameter is 19 millimeters, divide that by 1,000, so 0.019 meters. And the Poisson's ratio is 0.35. So calculating the area, and I converted this already into meters squared. So 2.84 times 10 to the negative 4. So really, really small stuff. But at least now we're all in the correct units. So if we plug all of this in, it looks really crazy at first, but just, it's worth writing everything out to ensure that you're getting your answer in the units that you want. So we see that this meters squared will cancel out with that meter squared, and then we have this meter here canceling out with that meter, so the only thing left is Newton, because Poisson's ratio is unitless. So what we get from this value is P is equal to 14,093 Newton, or 14 kilonewtons. So this would be the axial force that would cause this copper rod with the geometry and material properties given to have a reduction of diameter of 0.003 millimeters. All right, let's look at a Hooke's law one, and this is actually a three-dimensional one. So we're told a rectangular block of aluminum with these properties given here, with the dimensions provided 50 by 50 by 100. It's placed in a pressure chamber, is subjected to a pressure of 100 megapascals. So we're asked, what is the decrease in dimensions of the longest side of the block, so that 100 millimeter side? So assume that the material remains in the linear elastic range, which is nice. We're assuming that the material is homogeneous and isotropic. So this is 3 dimensions, but we have an equation that does this. But let's first visualize what we're talking about here. We have this block. Essentially, there's pressure being applied on all sides of it. And when I say pressure, essentially what we're talking about is a stress, right? 100 megapascals. Pascal is a stress. So what we would call stress, some people might call a pressure. It's the same thing. So this is essentially talking about sigma being applied on all sides, and it's equal here. So 100 megapascals. So pressure chamber, it could be something being submerged underwater where the weight of water is going to cause a pressure. It could be something buried underground where the weight of the soil above it and below it and surrounding it will cause pressure. So it could be any of these things wherever we're putting this block of aluminum. I don't know why. I don't know where. Anyway, so let's visualize these axes here. We're talking about X, Y, and Z, these 3 dimensions. So the stress being applied to this block in all 3 dimensions are the same. So it's kind of nice. It's super equal, 100 megapascals in the X, Y, and Z direction. So what we need to do is we need to find the change in dimension due to 3D loading. So what we do is we use the 3D generalized Hooke's law equation. And just the generalized Hooke's law equation looks like this in those parallels and perpendicular signs. Really, that just means the strain in one direction is equal to the stress in that same direction minus the Poisson's ratio times the addition of the 2 stresses in the perpendicular direction divided by the Young's modulus. So we're looking at the longest side. So in this case, the longest side will be that Z direction. So the strain in the Z direction is equal to the stress in the Z direction minus Poisson's ratio plus minus sigma x plus y all over E. And since the material is a homogeneous anisotropic, the E is equal in all the directions. So EX is equal to EZ is equal to EY. So we can just use that in one term on the denominator. So what we do is plug everything in. Remember, mega is times 10 to the 6, but the 70 gigapascal is times 10 to the 9. So we need to account for that. So we have everything in pascals, so the pascals will cancel out. And what I'm doing is just, since this is 100 plus 100, you can see what I'm doing there. Just already added that there. 100 plus 100 megapascals. What we see the strain here is 0.00486. This would be pascals over pascals, inches over inches. It's a unitless number here. But remember, what we need to find is the change in the dimension. So we can't just plug in strain. We actually have to plug in and multiply it by the original length to find that change in length. So change in length in this case would be 0.0486. Now, the cool thing with this is, like, since we have this change in the z direction, we could technically do the same thing, same equation here, and find the strain in the x direction, the strain in the y direction. We can then find the change in length in the x direction and the change in length in the y direction. You could see where this would actually be pretty useful. We can actually find the change in volume after loading. So you could probably imagine that, you know, if this was a hollow box or something, and you had some type of like air, like let's say a submarine or something, and you know, you wanted to see how much the pressure would change for the people inside the submarine, you could actually calculate the change in volume and then the resulting change in pressure. So this is like one of the examples of this, the benefit of keeping things in the linear elastic region, but then also using the generalized Hooke's law. All right, so let's look at a phase diagram here. I'm sure everybody's already listening to this on 1.75, so I'm just gonna talk really slow so it actually goes back to 1.00 and you start getting confused. Just kidding, I don't even want to do that. All right, we're almost done here, so let's just chug along to looking at this phase diagram problem. So considering the alloy of the two soluble components, A and B, described by the phase diagram below, we're asked to determine the masses of the alloy that are in liquid and solid phases. So the given temp, we're just told that the total mass of the alloy is 500 grams. Component B represents 60% of the alloy, 25% of the liquid is component B, 75% of the solid is component B. Anytime you have a problem like this, there's always going to be a lot of information given in the problem statement. So what's best is to write it out specifically what is given to you, and just really understand what you need to find from that. So we're told that the total mass of our alloy is 500 grams. And we're told that the percentage of that mass that is B is 60%. So we could find the mass of B by multiplying 0.6 times 500. So we know that 300 grams of mass of this total alloy is going to be material B, which means 200 is material A, right? 300 plus 200, it's only made of two things, A and B, so we could find it that way. But what we're giving is everything in terms of B, so we'll just stick with B for now. Our percentage of liquid that is B, I'm using that small p just to kind of verify, or just to distinguish between, now we're only looking at the liquid percentage. So only that section that is liquid, because remember there's a liquid and a solid. So the percentage of liquid that is B is 25%, and the percentage of solid that is B is 70%. So what we need to find is the total mass of liquid and the total mass of solid. And remember, we're in that transition zone. So the mass of liquid will have part A and B, and the massive solid will have part A and B as well. So we know that the total mass, 500 grams, there's going to be mass of liquid and the mass of solid. So the mass of B total is going to be 300 grams. And within that B, we know there's going to be a mass of a liquid that is B and a mass of solid that is B, because we're in that transition zone there. So this is where we use this breakdown here. So essentially, we know that the mass of liquid that is B is 25%. So this is going to be 0.25 times the mass of liquid, or big ML. And then the mass of solid that is B is going to be 70%, or 70% of our total mass of solid, mass of solid is going to be B. So what we're doing here is we're just looking only at B. So looking at B here in this equation, we know that total is 300 grams. And then from our solid portion, this is going to be 25%. And from our liquid portion, 25, solid portion, 70%. So essentially what we do now is we set up the systems of equations. So we have this first one where we can solve for ML or MS, and we plug that into our second one here. So what I'm doing there is you can see where that ML was. I'm replacing it with a function from our total mass, where ML is equal to 500 grams minus MS. And so now we only have one function with one unknown. So we solve for MS, making sure to factor out, everything okay, and that the math is correct. And when we solve for MS, then we can easily solve for ML from our first equation here. And we get the mass of solid is 388.9, mass of liquid is 111.1 grams. That would be our answer there. All right, that's it. Remember to review these. Use this for your FE, use this for exam, or just for general recap on engineering materials, mechanics of materials, and stress-strain relationships. You can always email me if you have any other questions or want to review anything further. And remember, look these up too. There's plenty of other example problems, things on YouTube, better explanations and videos than what I was able to do. So don't be afraid to Google, Google wisely. Good luck with this, and let me know if I can help or answer